Now I will show you a set of operations, both for transformations and actions. Right. I will show you the some commonly used operations in PySpark. So let's start with map. So the functionality of map is basically just the map function as we have introduced before. So virtually it will return a new RDD by applying a function to each element in the input RDD. So here we use RDD1 as the input RDD, and we need to define the function within as the input as the parameter of the map method. So one way to define the function is to use lambda. So here we just we want to write sort of like a word count method. So we simply do this. So for each element in RDD1, we create a tuple with x and a key value pair, where the key is the word and the value is 1. So if we collect, we can see all the key value pairs. Here, in order to view the contents within a RDD, collect will show all the contents as a list. We can also use take with a number, so it will only show a list of the top 4 top k elements within that RDD. All right. Okay, so this is a map, and the second one is flat map. So in order to do flat map, we need to define the text here as, for example, here, and we generate the RDD2. Sorry. So basically, the RDD2 contains 2 strings. All right. So let's write a map function. The map function is to is to tokenize the strings, which we will do it. Okay. If we use map, then you will see the result RDD contains 2 lists, where for each list there is 2 or 3 words. So the reason of that is the map function applies the map function applies the function to each element in this RDD. So for the first element is a word count. So the function is x.split. So it will tokenize the phrase here, and it will do the same thing for the second one. But sometimes we do want, for example, let's think these are 2 sentences. Okay, if we want to do the word count, we do want that. So these words are tokenized and within one big list. Right. So this is what flat map do. So for flat map, you basically write the same thing. And as you can see, it will, so the flat map will flatten the results. So from several small lists to a big list, okay, to a whole list. So this is what flat do. Next one is filter. So basically filter is to only keep those elements that satisfies the function here. All right, so for example, let's say the function is, so this here what we want to do is to filter all the words that is count. So we want to keep the words that is not count. Okay, we want to prune the words that is count. Yeah, so that's what you've got. All right. Now let's look at some narrow transformation functions. So start with reduce by key. All right. So reduce by key, the functionality is to merge the values for each key using using the input reduce function. All right. So here the input RDD of reduce by key should be a list of key value pairs. Right. For example, if we want to do a word count here, we can try this. So it's RDD reduce by key equals to RDD map reduce by key, where the is. So here in RDD map we actually have already count. I mean for each word it's a key value pair with the key is the word and the value is 1. So here we need 2 variables, and we return the sum of it. So the result would be the count for each word here. So that is reduced by key. And for sort by key, it's kind of easy. So you basically sort the RDD, and so based on the key value. For example, let's use RDD flat map. So it's sort by key. So as you can see, the words are sorted based on the alphabet order, right? So next one is group by key. So group by key, the functionality is to group the values for each key in RDD into a single sequence. So you can imagine here, this is RDD map where we already have a set of key value pairs, and if we use group by key, then this is the two is here would have would be merged together, and the values would be merged into a sequence. All right, so it's different by different as a reduced by key. Here we just add the values. So if we let's try group to RDD map group by key. All right. If we output the result of group by key, you would see that here the first one is the key, all the keys here. But for the second one in the tuple is PySpark iterable result. So it is not. So if in order to view that, you need to output all the elements in that sequence. So it should be something like this. And this is what group by key did. All right. So here, as you can see, many transformation functions would need a function here to tell the function what to do with each element in the sequence, or in RDD, because all these transformation functions is just like a map. All right. So now, in order to pass the function as a parameter, there are several ways to do it. Let's just use this as an example. So what I have been showing is to use the lambda, right? And if the function is complicated, you could try something different. For example, you can define operation here. And you can use OP to replace that's lambda. This is one way to do it. Another way is to write a function here. For example, we define a function and input and output, and we return x plus y as the result. Okay, we pass the function to the reduce by key method, and we could get the same result here. All right, so this is several ways of doing this. Now let's look at some action operations. We have already seen collect and take. These are two action functions. And now let's look at reduce. All right, so recall that RDD is a data. Is a list of 1 to 99, the numbers. Now let's do reduce. So use RDD's reduce. Let's do the sum of all the elements within RDD. All right. So in order to do that, okay. So this is a sum from 1 to 99, right? And we also have a count, which returns the total number of elements in the RDD. For example, count. Yeah, what we would have is 99 here. All right, so let's stop here for now, and we we probably will see more operations and functions of PySpark later in this course. For example, in the labs or in the lectures, when we explain MapReduce, we probably will write some more code. So, well, just in case someone asking for this notebook, I do suggest you, because you can see all the typing that I have been doing. It's better for you to try it on your own machine, and also you can search for PySpark API. I think we have a link on the web page of the course under the outline of the course. So basically, there are more functions, and you can try them, and you can try to build your own MapReduce program. It would be a nice practice, right, and prepare for the projects. All right, so let's go back to the slides. All right, so now we have introduced RDD and some operations over RDD, which are transformations and actions. Now let's look at some concepts regarding to RDD and Spark. So first is lineage. So if you still remember, for transformations, they take RDD as input and they output RDD, right? And where the RDD comes from can either from a transformation as a result of transformation, or it is created either from parallelizing an existing collection in your driver program, or referencing a dataset in an external storage system. So apparently, I mean, this relationship between RDDs exists all over the Spark, right? So RDD lineage is the graph of all the ancestor RDDs of an RDD. All right. So it also called the RDD operator graph or RDD dependency graph. So let's let me show an example to you about this lineage thing. So let's say R1 is initialized by parallelizing, right? And let's say R2 is from R1 dot map. We omit the function inside the map just to show the relationship between R2 and R1. Let's also define R3, which is from text. Okay. And say R4 is from R3. And let's say R5 is R2 join R4. Right. And finally, R6 is R5, let's say filter. All right. So in this case, we do have the relationship between all these RDDs. Well, if we draw the graph here, remember the nodes of the graph is RDDs, and the edge is the dependencies between RDDs. So the graph should be directed, because this dependency is has the direction, right, from parents to child. So you have R1 and R3, they are initialized either from the driver program or from the file in external storage system. So they are kind of have no parents here. So R2 is R1's child, and R4 is R3's child. And for R5, it is the child of R2 and R4. And R6 is R5's child. So if we want to have the RDD lineage for R5, let's say, then we don't need R6 here. So R5 is sort of the endpoint of the graph, right? And we need to have all the ancestors of R5 within the graph, and as well as the relationships here. So to conclude, RDD lineage is like a logic execution plan of until the current RDD, and how to generate such kind of RDD lineage. So basically, while we create a new RDD, if it is from an existing RDD, then the new RDD will also carries a pointer to its parent RDD. For example, when we initialize create R1 and R3, because they have no parents, so we will do nothing. But when we have R2 here, because it is created from R1, so there will be an edge here. And when we create R4 and R5, so on and so forth. So this is RDD lineage. So why do we need such kind of things, right? So the main purpose of having a RDD lineage is to guarantee the fault tolerance of RDD. So basically, if the RDD is generated from fault tolerant data, then it is fault tolerant. That is kind of easy to understand. I mean, just think of if the RDD is generated from a file in HDFS, then if this RDD is lost, then we can recreate it from HDFS, because HDFS is fault tolerant. Therefore, such kind of RDD is fault tolerant. Now let's consider if a worker fails. We know that in Spark, RDD is split into partitions, and each node, or say executors, is operating on a partition at a time, right? So, well, theoretically, I mean, each executor can be assigned multiple tasks. I mean, if it has multiple cores, and the number of partitions is relatively larger, yeah. So, but when such kind of node who is operating on a specific partition of an RDD fails, then that part of data or RDD will be lost. Right. So in order to handle such case, because we know that there is a series of functions, either transformations or actions, that are executing on this partition of the RDD. So these operations, as shown in RDD lineage, they have dependencies between them. So basically, if a particular node fails in the middle of, let's say, an operation in operation C, let's say. Let's say it fails when it executing C, but we know that C is from B and B is from A. So the cluster manager will find out the node is failed and tries to assign another node, a new node, to continue the processing. Well, the new node will be told to operate on the particular partition of the RDD, and it will also be told of the series of operations A to B to C here. So this is the lineage that of C. All right. So the node can redo the procedure here and recover C. So there will be no data loss. So as we have explained here, so the partition can be recomputed from the original fault-tolerant dataset using the lineage, and the task will be assigned to another worker. By the way, here I forgot to mention that you can actually view the lineage graph of an RDD using, for example, R5. It's to debug string. Well, you can use this method to print the RDD lineage graph. All right. So now we know how the fault tolerance is guaranteed for RDD. Be aware that here we only discussed the case of the failure of the worker node. So how about the failure of the driver node? If the driver node fails, then basically because the driver node is running the Spark streaming application and the Spark context, so basically all the executors will lose their in-memory data. So in order to prevent that, for example, Apache Mesos, which is an open source project to manage computer clusters. So it will maintain a backup driver node such that if the driver node it failed, the fault tolerance is still guaranteed. All right, so that's the fault tolerance of RDD and as well as well. Now let's look at DAG. So DAG is an important component in Spark. Actually, according to the textbook, DAG and RDD are the two core components of Spark. So DAG is a direct graph with no cycle, or say directed acyclic graph. So since it is a graph, so basically the node is either RDD or the result, and the edge is the operation to be applied on the RDD. So you can imagine that as the example that we have mentioned before here, Right, if we add R7 is, let's see, R6 dot reduce, right? And the DAG is pretty much like this, right? So on the calling of action, and remember we always have only one action, the created DAG submits to a DAG scheduler. Let's talk about DAG scheduler later. Let's look at let's first discuss the created DAG. So basically, the DAG is created on the calling of action. If you still remember, we have talked about the lazy evaluation for a couple of times. So here, DAG is highly related to the concept of lazy evaluation. So basically, the DAG is created on the calling of action, means during all the transformation operations, there is no DAG created. Here we better understand this in the context of Java, because Spark is originally written in Java. So it's not like the notebook, in the notebook as we have shown before, because in the notebook, every time we call a transformation function, we will execute it. But in Java, because Java is a compiled language, so basically it will see all the whole procedure, right? And the DAG will be created on the calling of action. Now, when the DAG is created, it will be submitted to a DAG scheduler, and the DAG scheduler will further split the DAG into the stages of the task. And then the stages are passed onto the task scheduler. The task scheduler launches tasks through a cluster manager. Although the dependencies of stages are unknown to the task scheduler. And finally, the workers execute the tasks. All right, so now the problem is what is the stages? So the DAG scheduler will split the graph into multiple stages. Stages are created based on transformations. What does this mean? So there are two kinds of transformations, the narrow transformation and the wide transformation. So the narrow transformations will be grouped together into a single stage, and the wide transformation defines the boundary of two stages. So if you still remember, the narrow transformation, well, there involves no data shuffling, and the wide transformation involves data shuffling. So as long as the data are not shuffled, so this partition of data, after a narrow transformation, the data will be still in this partition. The result of the narrow transformation on this data partition A will not involve any data from data partition B or C. So it can be serialized. Now here, if we see we have some data here after a narrow transformation. and they may go through some data shuffling. Then we say this part is one stage. If here another data shuffling happens, so we take this part as another stage. But if there is no data shuffling, means another narrow transformation, then the third stage will be from here until the next wide transformation appears. All right. So now we have these stages. The DAG scheduler will then submit the stages into the task scheduler. So the number of tasks actually depends on the number of partitions. When we're talking about the original RDD created from HDFS, for example, and if it is parallelized, then the number of partitions is user defined or use the default value. So anyway, I mean, there is a number of partitions, and here the number of tasks depends on the number of partitions, and we have explained the reason of it. All right, so here the DAG brings the other another advantage is that the stages, that if they are not interdependent, then they may be submitted to the cluster for execution in parallel. This and another thing together makes the DAG operations can do better global optimization than other systems like MapReduce. So we will explain this too, as the reason here and another reason on this slide. So basically, in this slide, interdependent means if we have a stage 1 here and stage 2 here, if there is no data flows between 1 and 2, on the other hand, the data from 2 and 1 finally all goes to 3. Then 1 and 2 can be executed in parallel. So this is one way to optimize the DAG operations. And the other thing is that, for example, if we do a map first, followed by a filter, then we actually can switch the order. We do filter first, then map. In this case, the complexity of filter operation is always the same. Let's say we have n nodes, n elements, and after the filter we can we have half of them. So if we do map first, then do filter, then we will do map for n elements and do filter for n elements as well. But if we do filter first, then it's for n elements, but the map operation, we only need to do it for n over 2 elements. So in this case, we kind of reduce the cost of the execute this stage. All right. So this part is a little bit like what we do for SQL query optimization in DBMS. So the idea is similar, and the reason that we can do this is because a DAG actually offers the structure of these kind of operations how the relationship between them. So we can cut them into stages, and then we also can do the parallelising or switch the order of two transformations. And for lazy evaluation, I mean, at the current stage, I think you can appreciate the goodness of lazy evaluation. You only act until you see the calling of action, and you create the DAG. You split them into stages, and for the task scheduler, also you can do some global optimization for the whole task, which is the other systems like MapReduce cannot do. All right. So now let's look at the relationship between lineage and DAG. So the common thing of both of them is that they're both DAG, directed acyclic graph as a data structure. All right. So yeah, so here should be a DAG in Spark. Okay, I will fix that later. But they do have a lot of differences. So for the first of all, the end node of lineage and DAG are different. So the DAG, the end node of DAG is usually an action. And the end node for lineage is RDD. Also for a job, right? For a job, there would be only one DAG. However, there would be multiple lineages. Depends on I mean, for each RDD there is a lineage. So that's the thing, and therefore they place different roles in Spark. For example, for DAG, the main purpose of having DAG is to do the to split the task, to split the whole procedure into several stages and pass to the task schedule. And for so this is for the lazy evaluation. And for lineage, the main purpose of lineage is to keep the lineage for each and every RDD such that to guarantee the fault tolerance. So they have they place different roles in Spark and serves different purposes. So the lineage and DAG are usually totally different, especially, I mean, yeah, especially considering the end nodes. So there is only one case that they will be the same, is that your Spark program is to create only one RDD, and it's the last step. Then the whole DAG is a lineage of that RDD in the last step. So only in this case, they are the same. Now let's take a back look at the Spark architecture again, where I believe you will have a better understanding of all these things. So the one thing that I want to point it out is for the DAG scheduler, and the task scheduler, they all live in the driver program, not in the cluster manager. All right. So the cluster manager does nothing but offering resources like CPUs and RAM. So once the Spark executors launch, they directly communicate with the driver to run, or with a Spark context to run the tasks. That's why you can see this two arrows here. So they do have a direct communication. The cluster manager only manage RAM and CPU for the task. All right. So now you can see how you initialize your task by creating the Spark context, and how the thing's going. We've shown a few examples there, and how DAG scheduler and the task scheduler will divide it, the whole task or the whole procedure into several stages, and assign the jobs to the executor. So these are the assign the tasks, right, to the executor, right? And also, I mean, what if one worker node failed? How they guarantee the fault tolerance? So that's pretty much for today's lecture. I've noticed that today's lecture is kind of shorter than usual. This is because we kind of finish the introduction of Spark and RDD and DAG here. So we will start a new topic from next week. So it's better to stop here. So please use the extra time to try the different transformation functions and action functions. You will use them in the following projects and labs. All right. So that's all for today. Thank you for watching. See you next week.